Okay, so we're going to continue on in chapter 2, and we're going to be looking at the second lecture, the second PowerPoint in our learning plan. And we are going to be paging to section 1013, which is all about gear trains. So you can find that on page 288 in your book if you're following along. Now, a gear train is going to be a series of mating gears used to achieve larger speed reductions. So, for instance, if we have our input maybe coming off of a motor or a gas engine is 1800 RPMs, and we want to reduce that speed on our output down to 10 RPMs, okay? That would mean that our velocity ratio in one set of gears would have to be 180 to 1. So, for instance, if we would have a 6-inch pinion coming off of our input, whatever we have as the gear, we would multiply that by 180, and that's how much larger that gear would be. It ends up being unreasonable in a lot of cases when we have larger gear reductions like this or speed reductions to economically and also feasibly have a nice compact design, okay? So what we end up doing is we end up putting reductions next to each other. So we'll kind of break it down into levels. So we might do 3 to 1 in one, then 6 to 1 and 4 to 1, and we would kind of gang them together. Chris's question is there a difference between a gear train and a gearbox? And the answer is there's a gear train inside of the gearbox. So when you have a series of gears that are reducing the speed for something, there are multiple sets of gears in there that are going to do that for us. So there is a train inside of there. Okay. So we're going to be looking at example 1018. And I want to kind of just peek there before we do the actual example, but this would be an arrangement of a train, okay, a gear train. So what we have going on here, our input is down here at gear number 2. This is a front view where we see the circle views, if you would, of the pitch diameters of each one of our gears. And if we look directly above, that's going to be your top view. So we can see that this is the shaft, in line. So all of these are in line with one another. So as we look here, we're going to notice that we have sets of gears that are engaged. This is going to be our first velocity ratio in our train. The next one is going to be, as we look at the top here, this is going to be our next velocity ratio. And then we have a third velocity ratio. So as we look from the front view, you'll notice that gear 2 and gear 3 are in engagement with one another. We don't see the teeth overlapping here. They're just showing the pitch diameters tangent to one another. So the teeth would overlap one on the other there, okay, where they would actually engage. So we've got 2 and 3 that are going to be engaged. Then you'll notice that if we go forward on that same shaft from 3, this is going to be 4. So I'll label this. This is number 2. This is number 3 in that arrangement, okay? Then number 4 is directly in front of 3 on the very same shaft. They are going to be going at the same angular velocity. Okay. Then 4 is right here in the front here, is engaged with 5. So this one is going to be number 5 as we look on the top. Then on the same shaft as number 5, forward is going to be number 6. So right here is number 6. And then 6 is engaged with number 7, okay? So this arrangement right here, we've got multiple velocity ratios. So this would be velocity ratio, if you would, number 1, velocity ratio 1. Then these two is going to be velocity ratio number 2. And then we have a third velocity ratio, number 3, okay? Each time we do a velocity ratio, we have a reduction. So in this case, we have 3 reductions. This would be called a triple reduction. Sometimes you hear double reduction. That would mean that there would be 2 sets, okay? You can have quadruple reductions, all right? So, but the important part here is that instead of having something, for instance, like we had that example where if we have 1800 on the input and we want to get 10 RPMs on the output, instead of having a smaller pinion gear and then having something 180 times that number, you can see that we get the same thing done in a series of reductions or velocity ratios here. And we have a shorter or a lower profile of room that we're going to actually take up to achieve that reduction. Okay. Now, how do we calculate trains? All right. There is an equation for trains, and that equation is right here, 1035 in our book on page 288. So what we're going to do is we're going to add train value, TV, to our equation sheet. So TV, which is going to be train value, is going to be equal to, now, many times, one of the things that we want to know is when we look at the train, we want to compare the very first input gear on our train, how fast it's going, to the output gear. So in the case of the example we looked at here, our input would be number 2. And we want to know, okay, in comparison, what is the angular velocity of number 7? They're not directly related, but that's usually something we want to know. So we're just going to go our angular velocity in compared to or in ratio to our angular velocity out. So that might be, in this case, gear 2 to gear 7. Okay, so this would be 2 on top and 7 on the bottom. All right, but we can also calculate it, and we do calculate it with the individual velocity ratios, however many there are. So we are going to put a negative in front of each one of these velocity ratios. We're going to say negative velocity ratio number 1 times negative velocity ratio 2, make a little bit of room here, times negative velocity ratio 3, and then we would kind of, however many there would be. So if there would be multiples more than 3, we would continue to do that. I'm going to explain the negative in just a little bit. Is that what you're going to ask? Yeah, because it's not in there. They sneak the negative in the problems, but I like the negative. I'll tell you why. The negative value here is a signal to us, and it gives us the indication if the input is going the same direction as the output, okay, without having to manually change the directions each time, okay? So for instance, when we have 2 gears at our engagement, we know that from the input, for instance, on number 2 here to the output, okay? So in this problem, I just want to take a peek. I forget. We have gear number 2 is going counterclockwise. So that means it's going to be going in this direction right here. Okay. So W2 is going to be counterclockwise. Whatever gear it's engaged with, in this case, number 3 is going to go in the opposite direction. So the angular velocity of number 3 is going to go clockwise. So any 2 that are engaged are going to be opposite direction. Now, as we go forward on the same shaft, number 4 is mounted to that. So number 4 is going in the same direction as number 3. They're keyed, if you would, on that same shaft. So they'll be going in the same direction. Now 4 is engaged with number 5. So that means that 5 is going to come back in the opposite direction and go counterclockwise. You'll notice that 6 is on the front of and on that same shaft. So it's going to go counterclockwise. And now 6 is engaged with number 7. So it'll go in the opposite direction and go back clockwise. Okay. Now I had to do that manually. If I had then more velocity ratios or more reductions, I would have to continue to do that. This negative sign does this for us. So for instance, when I take the velocity ratio 1 times velocity ratio 2, because the negative is in front of there, what's going to happen is they'll multiply together, and positive means that they're going to be going in the same direction. Okay. When I multiply by 1 more, it's going to go back to negative, and negative means it's going to be opposite direction. So what that means is when I compare my input to my output, if I end up with a positive value for my train because of the negatives in front of each one of the velocity ratios, that means that the input and the output are going in the same direction. So if I'm counterclockwise on my input, my output is going to be counterclockwise. And we see that, for instance, right here. Here's velocity ratio number 1, okay? Velocity ratio number 2. And if I look here, if I go from 2 to 5, they're going in the same direction. Do you see that? All right. So instead of having to go through and manually draw each direction going back and forth, by putting the negative in front of each one of our velocity ratios, it does nothing more than to tell us at the end of the train, are we going in the same direction or are we going opposite? That's it. Okay. So that's why the negatives are there. You're going to see that in the example problem, although they don't add it to that formal equation. Okay. So over on the right-hand side, you can say that TV is equal to train value. Okay. Train value. That's it. It is unitless. It's unitless because we're multiplying together velocity ratios. And as we know, velocity ratios are unitless because they're always going to have their units cancel out top to bottom. Okay. All right. So that's the last equation on our sheet. Okay. So let's look at our first example here, which we've already kind of introduced, but let's formally go to the problem statement, which is at the top of page 289. Okay. They're giving us some information here about each one of the gears. So we'll go back to that in just a bit. But ultimately, using that information above and the arrangement that we see on the previous page, we want to determine the rotational velocity of gear 7. Okay. So that's going to be W7. That's what we want to find. As gear 2 drives at 1800 RPMs, so this is going to be our W2, counterclockwise. All right. So that's the first thing we want to do. So knowing that this is going at 1800 RPMs counterclockwise, how fast is this one going? They're not directly, connected. So we've got to go through our train, if you would. And then the other thing that we want to determine in this example is we want to know what is the distance between the shafts, or the center distance between gear 2 and gear 7. So how far apart are these two centers? All right. So those two things, that's what we're going to find. So what did they give us? We got the arrangement here, which we've talked about, but now they give us the information on the top here. The two, I want to kind of identify first the gears that are engaged. So we've got gear 2 and gear 3. This is going to be our velocity ratio number 1. Okay. Gear 4 and gear 5, these two are engaged. That's going to be our velocity ratio number 2. And then gear 6 and gear 7 is going to be our velocity ratio number 3. Okay. Now, thinking ahead here, we need to find the W7, okay? The angular velocity of 7. So there are multiple ways that we can get at that. But what we're going to be doing is we're going to be working through our velocity ratio equation, okay? Now, because we also have to find center distance, and center distance is related to the pitch diameter, okay? The diameter across the effective, pitch circle, if you would, of the gears. What we're going to do is we are going to calculate the pitch diameter for each one of these gears so we can use that in turn to get our center distance. It'll just be easier. We could do any one of the other numbers. We could do number of teeth, whatever it might be. But to be consistent and just thinking ahead, if I didn't need to know the center distance, I might approach it a little bit differently. But I'm going to find the distance, or the pitch diameter for each one so we can get the radius, which then ultimately gets us to our center distance. Okay. So given the information that we have here, what I'm going to do is I'm going to start our problem and I'm going to look at it ratio by ratio. Okay. So looking first at velocity ratio number 1. I'm going to zoom out here a little bit. So this is example 1018. Okay. 1018. And we're going to be looking at velocity ratio number 1, which is gears 2 and 3. Okay. And they're 2 and 3 identified in the problem. Okay. Now, when we look at what we are given for gear number 2, we're given the number of teeth and the diametral pitch. And for gear number 3, we're given the pitch diameter. Okay. So I'm just going to write that down. So N2, number of teeth on that gear is 12 teeth. And diametral pitch is going to be 12. And I'm going to put our units in there, even though they don't give them to us, because remember, they're not going to give them to us and we don't really report diametral pitch with anything but the number. But when we do our our work and our equations and we need to use it, we do need to put it into practice, if you would. And then for gear number 3, they're giving us the pitch diameter number 3 as 2.5 inches. Okay. Now, like I said, each one of these gears, we want to find the pitch diameter for. So we know the pitch diameter, it's given to us for 3. So we're going to be using that. But we need to figure out what the pitch diameter is for number 2. Okay. So if we look at our equation sheet right at the top, this is going to be our relationship between the number of teeth, the pitch diameter, and the diametral pitch. So we want to solve this for the pitch diameter, which is lowercase d. John, I saw that you just came in. We're doing example, as you can see, 1018, and it's found starting on page 288. So let's, using that equation, I want to solve for the pitch diameter for gear number 2. So I'm gonna actually write it in the form so that I have D is equal to, D2 is going to be equal to the number of teeth on 2 divided by the diametral pitch. Okay, it's just taking that equation and rearranging. And now I'm going to put my values in. So I know that there's 12 teeth in gear number 2, and the diametral pitch is going to be 12 teeth per inch. Okay, teeth cancels out. My D2 is going to be 1 inch, right? 1 inch. Okay. So that's my first set. All right. So my next set, we're going to look at velocity ratio number 2, which is going to be gears, 4 and 5. Okay. So gear number 4 is on the same shaft as 3. Okay. So it's sitting in front here. All right. And it's engaged with number 4. So we want to find out what is the pitch diameter for each of those. So if I look at, go back up here at the top of page 189, gear 4, we know that there's 15 teeth. Gear 5 has a pitch diameter of 3 inches and has a diametral pitch of 10. So I'm going to write those down. So I know that N4 has 15 teeth. Okay. And D5 is 3 inches. And the diametral pitch of gear number 5 is 10. And that would be teeth per inch. Okay. Now, we know pitch diameter, right? We're trying to find the pitch diameter for each one of these. So we know the pitch diameter here, so we have to find the pitch diameter here. Now, as we can see up here, we can use that same form. So this would be D4 is equal to N4 divided by the diametral pitch. Now we're given N4, but do we know the diametral pitch for number 4? How do you know it's 10, Josh? Yep. Remember, any 2 gears that are enmeshed with one another have to have the same diametral pitch. So just because gear 5 has a diametral pitch of 10, gear 4 has to have a diametral pitch of 10. So that's going to be the diametral pitch. So we're going to do 15 teeth divided by 10 teeth per inch. So teeth cancel out. We have the inches in the denominator of the denominator, which means it multiplies on top. So our D4 looks like it's going to be 1.5 inches. Okay. So now we have the diameter for number 4. We have one more. Okay. So the last 2 gears that are in mesh are 6 and 7. And up here, we have the information for gear 6 and 7. 6 has a pitch diameter of 1.5 inches, diametral pitch of 8. And number 7 has the number of teeth of 32. So trying to sneak this in at the bottom here, velocity ratio number 3, which is equal to gear 6 and 7. We know that the number of teeth on 6, pitch diameter 6, D6 is equal to 1.5 inches, and the diametral pitch of 6 is 8. Okay. then telling us that the number of teeth on gear number 7 is 32 teeth. Okay. So we need to calculate the pitch diameter, D7. I'm going to try to sneak this in here. D7. So using that same format as the one above, this would be N7, which we know, divided by the diametral pitch. Notice that 6 and 7, again, are engaged with one another. So the diametral pitch is going to be 8, right? So that's going to be 32 teeth divided by 8, and that's teeth per inch. So that cancels out. My D7 is equal to 4 inches. Okay. And there's my 6. So now I have all of the pitch diameters for each one of my gears. Any questions on that? This is going to be very similar to one of your homework problems, one of the last two. Okay. All right. So now that I have those, and since I have all those diameters, I'm going to go ahead and do the center distance right away. Okay. So center distance is simply going to be, since I know all of these diameters, it's going to be the radius of 2 plus the radius of 3, the radius of 4 plus the radius of 5, the radius of 6 plus the radius of 7. Okay. Or I can add all these diameters together and just simply divide by 2. Okay. So that's what we're going to do. So on the next page, I'm going to have C is equal to, and this is going to be diameter of 2 plus diameter of 3 plus diameter of 4 plus diameter of 5, diameter of 6, D6 plus D7. And we're going to take that all after we add them all together, and we're going to divide by 2, and that's going to be my center distance. Okay, it's the radius of each one. So let's put our values in. So D2 was 1 inch, D3 was 2.5. So 1 inch plus 2.5 inches. Plus D4 is 1.5. D5 is 3. 1.5 inches plus 3 inches. Plus 6 and 7, 1.5 and 4. And then we're going to divide that all by 2. So tell me what you got for your center distance. I'm going to grab the chat box out in case anybody comes up with an answer or a question. You get 6.75. Isaac is nodding his head. Chris is nodding his head. Awesome. Lex, good. Good. Got it. Thank you, Jack. So what we have then is when we look at the space that we need 6 3/4 inches between these two centers. Okay. All right. Now the train value. Okay. Now, as we know, the train value, sorry, TV, not VR, TV. It's going to be equal to W2 over W7, okay? But we need to find the train value first. And we're going to try find the train value by taking those individual velocity ratios, okay? So we're going to take negative VR1 times negative VR2 times negative VR3. They are not added together. They are multiplied together, okay? So now to find the velocity ratio, as we had looked at before, we're going to use in the set the gear pitch diameter divided by the pinion pitch diameter, okay? So what that means is we are going to take, okay, they're negative out front here. So for velocity ratio number 1, that was gears 2 and 3. 2 is the smaller, is the pinion, and the gear is the bigger one. So we're going to take 2.5 inches divided by 1 inch, okay? Negative 2.5 inches divided by 1 inch, okay? So this is, and I'm going to put this inside. I don't want to put it on the outside. It's not an operator, it's a sign. Okay. Then we're going to take our second velocity ratio. Second velocity ratio is here. Gear 5 is the bigger, so it's going to be on top. So it's going to be 3 inches divided by 1.5 inches. Negative out front. Okay. And then the last one is going to be 6 and 7. 7 is 4 inches, so it'll be on top, and 6 is 1.5, it'll be on the bottom. Okay, now each one of these units cancel as we are expecting because it's a velocity ratio. So our train value is going to be multiplying each one of these together. And you'll notice that with the negative signs here, we're going to end up with a negative in front of our train value, and that'll come in handy in just a bit. So let me know what you get for your train value here. Got 13.333, which the book has, so that looks like a good number. 13.333, and unitless because our units cancel top to bottom. Thank you, Christian. You got it too. Awesome. All right, now we know that that number we can set equal to W2 over W7. So we know what W2 is. We know that it is 1800 RPMs. We know our train value is negative 13 1/3. Our unknown is W7. Okay, so we're going to rearrange this just so that we can solve for W7 is equal to simply going to be W2 over that train value, right? So now we can put in our numbers, 1800 RPMs divided by negative 13.333. So W7 is going to be equal to a negative 135 RPMs. Now, this negative just says that it's going opposite of whatever our input was, which was W2. So this is going to be opposite direction to W2. So you always have to add on what is your direction here, okay? So if our W2 was counterclockwise, then this is going to be clockwise, and that will be your answer. Okay. Does that make sense to everybody? So the negative there is purely for determining what the direction is in relationship to your input on the entire train. Okay. It does nothing else. All right. Questions on that one? This is going to be exactly like your 1050, I believe, is the problem. Okay, so this will be your example for that. All right. Then let's go back to our PowerPoint presentation. We talked about train value. We did example 1018. So the next subject that we have here in the next section is called idler gears, okay? Let's look at idlers. So we're going to turn the page and we're going to look at page 290. Okay. So this section right here is 1014, idler gears. Now, I'm going to tell you something about idler gear. The sole purpose of an idler gear is to change the direction of the train. It will not affect the train value. The only thing that it's going to change is the center distance because we have to insert it, so it's going to get a little further apart. But its sole purpose is to change the direction of rotation from the input to the output, okay? So in this case, we could scooch 2 and 4 together and get the same velocity ratio or train value. It won't change the reduction that occurs. But what it does do is it changes the direction. So if we look here, if, for instance, we say W2 is going clockwise, then W3 is going to come back counterclockwise, and then W4 is going to go back clockwise again, okay? Now, like I said, it adds to the center distance, but it does not change the train value, and let's see why. So what I'm going to do is I'm going to go down below here, and we're going to figure out our train value. Okay, so our train value from 2 to 4 is going to be equal to velocity ratio number 1, which is going to be these two, 2 and 3. Okay, put a negative in front of there, times a negative velocity ratio number 2. Okay, now again, these negatives in front are just so that we can determine if we're going in the same direction or in opposite. So now we know that we can also find the velocity ratio by taking the gear, which is going to be D3, divided by the pinion, D2, which are the pitch diameters. And they give us the pitch diameters for each one of these. That's why I chose the diameters. Times the negative, and this time it's going to be, our gear is going to be diameter 4 divided by diameter 3. Okay. Notice if I multiply across the top, divide by the bottom, what happens to the diameter 3 for the train value? It cancels out. It cancels out. It has no bearing on the train value whatsoever. Whatsoever. The negative signs are going to multiply together, and now these are going to go in the same direction because there's 2 reductions. So these would multiply together. We would get a train value of, and we can calculate it. It's going to be a negative 6 over 2, right? Inches, times a negative 8 inches over 6 inches, right? So again, the 6 would cancel train value wise, and it would simply be 8 divided by 2. And the negative times a negative is a positive. So we would have a positive 4 for our train value, which would mean that gear 2 is going in the same direction as gear 4, or I really should say the output is going to go in the same direction as the input. Okay. So train value wise, the idler does nothing, absolutely nothing. Center distance wise, yes, and direction wise, yes. Okay. So let's look at an example with an idler gear in it to see how we handle it. We'll do a similar example to the last one that we did, but it'll have an idler. So they don't have an example in the book, so I picked for us to do as part of our practice problems. Our last practice problem is going to be 1053. Okay, 1053. So we have a gear train here. It's shown directly above. The gears have the following properties. They're giving us the number of teeth, diametral pitch, or the pitch diameter for each one of the gears here. Okay. Now, what I want to show you is where this idler is. So we start out, our input is going to be on gear number 2, and it tells us that gear number 2 drives at 1200 RPMs counterclockwise. So that means that gear number 2 is going in this direction, W2 right there. Okay, that's our first gear. Now it is engaged with gear number 3. So that's going to be our first velocity ratio number 1. Okay. Now we don't have a top view, but directly in front of it on the same shaft is gear number 4. Okay. Gear number 4 is engaged with gear number 5. This is going to be velocity ratio number 2. So 2 and 3, 4 and 5. Now, directly across, 5 is also engaged with number 6. So this is going to be velocity ratio number 3. Sorry, not number 2, number 3. All right. Notice number 5 is engaged with 2 gears. That's our idler in this train. Okay. And then the last velocity ratio we have is number 7 to number 8. So this is going to be our velocity ratio number 4. Okay. Now, when we do our train value, we'll put a negative in front of each one of those velocity ratios. So we'll kind of do that here. So velocity ratio 1 times velocity ratio 2, it's going to be a negative times a negative becomes a positive. Times a negative, we'll go negative, and it'll become positive again. Do you see that by multiplying that 4th time? So we should end up with W8 going in the same direction as W2. We'll see. We should. All right, so we are going to do this problem very similarly to the last problem, because what they're asking for is determine the velocity of gear 2. So gear 8, we need W8 as W2 goes 1200 RPMs counterclockwise. Also determine the center distance. Okay, so since we have to find center distance, we're going to say take that same approach as last time, where we want to find the pitch diameter for each one of our gears. Okay, because then we can just, use those for that center distance. So we're going to start off here with, so this is problem 1053. Okay. And we're going to start out and we're going to do the same process as we had on the last one. So we're going to look at velocity ratio 1, which is equal to gear 2 and gear 3. Okay. So they're giving us number of teeth, N2. It's going to be equal to 16 teeth and a diametral pitch of 16. And we know that to be teeth per inch, right? And then gear number 3 has a pitch diameter of 8 inches. D3 is equal to 8 inches. So this one's already done for us. And then we need to just find the pitch diameter of number 2. So we know that D2 is going to be equal to the number of teeth in gear number 2 divided by the diametral pitch. So it's going to be 16 teeth divided by 16 teeth per inch. Teeth are going to cancel. I'm going to put it on the same line. I'm going to go over here. D2 is equal to 1 inch, right? 1 inch. So that will be its pitch diameter. Then we're going to go to velocity ratio number 2, which is going to be gears 3 and 4. No, 4 and 5. Sorry, 4 and 5. 4 is in front. 4 is in front. Gear 4 and 5. Okay, so I'm going to scooch this up a little bit. I don't know if we can see this at the same time. I don't think we can as far as I'm zoomed in. But number 4 here, we have a pitch diameter of 1.5. So that's given to us. So D4 is going to be 1.5 inches. Okay. Gear 5 is 50 teeth and a diametral pitch of 10. Okay. So N5 is 50 teeth and a diametral pitch of 10. And that's going to be teeth per inch. So pitch diameter number 5 is going to be number of teeth 5 divided by the diametral pitch. So we know that to be 50 teeth divided by 10 teeth per inch. Teeth cancel, we're left with inches. So I'm going to do that very same thing. D5, glancing above. D5 is going to be 50 divided by 10. So it's going to be 5 inches. So here's our pitch diameter for 5, pitch diameter for 4. Makes sense? Any questions so far? All right, velocity ratio number 3. Okay, that is going to be, velocity ratio number 3 is going to be 5 to 6. So it's going to be gears, what? Gears 5 and 6. So we just calculated the pitch diameter of 5. We know that to be 5 inches. And in our problem, what do they give us for 6? The pitch diameter of 6 is 5.5 inches. So D6 is equal to 5.5 inches. So we have those already done. We don't need to do any recalculations. Okay. And then our last velocity ratio is going to be number 4, and that's going to be gears 7 and 8. Gears 7 and 8. Now, for gear number 7, they have it N7 is equal to 1.5 inches. That should be D7. That should be the pitch diameter of 7 is 1.5. That's a typo in the book. So D7 is equal to 1.5 inches. So that one's done. And then for number 8, they're giving us the diametral pitch is 8 and the number of teeth is 56. So N8 is equal to 56 teeth. And diametral pitch is equal to 8 teeth per inch. So we just have to calculate the pitch diameter for 8. So D8 is going to be equal to the number of teeth in 8 divided by the diametral pitch. So 56 teeth divided by 8 teeth per inch. So D8 is equal to 7 inches. Okay. So now we have the pitch diameters for all of the gears in the train. So just like last time, instead of waiting to do this, the center distance, let's do the center distance next since we have all these done. Okay. So I'm going to go over here. So we're going to look at our diagram because we have an idler. I want to see how that idler affects things. So my center distance is going to be equal to, so from the center of 2 to the engagement point is going to be the radius of 2, or D2 divided by 2, right? I cannot put a line underneath and do them all by 2 because the idler is a little different. So that's the radius of gear 2. Now, it's engaged with gear 3. So gear 3 from where it engages with 2 to its center line is going to be half of diameter 3's pitch diameter. So I'm going to go a little closer so I don't run out of room. D3 divided by 2. Plus, I'm on the center here. So now it's going to be the radius of D4. So it's going to be pitch diameter 4 divided by 2. Now to get from the point of engagement to the center of 5, so it's going to be plus D5 divided by 2. That's the radius on 1/2. Then I've got to go to the other side of D5 and take the other radius. So essentially, do you see how we can replace those 2 radiuses of our idler with just the diameter number 5? Yeah, that's the difference here. That's why we can't like take all the diameters and divide by 2 because there's the idler in there, because that one we have to do the diameter for. Then I'm going to go back to, I have half of 6, okay, plus the radius of 6, plus the radius of 7, plus the radius of 8. Okay, so just the one idler, which is D5. Okay, so now we're going to put all our values in. Okay, so this is going to be 1 inch divided by 2 plus 3 inches divided by 2 plus 1.5 inches divided by 2 plus 5 inches. That's for our diameter of gear number 5. Plus 5.5 inches divided by 2 plus 1.5 inches divided by 2 plus 7 inches divided by 2. Okay, so that right there is your idler. Okay. All right, so then what is our center distance for this one? We don't have an answer key. We don't have an example worked out. So we gotta plug it in. Is that right? Did you get 17 1/4? Really? Maybe I'm looking at the wrong problem. 14.75. Oh. Oh, that's why. I looked at it wrong. I don't know why I put 3. I glanced at it. That's why. I put 3. You probably put the right number. Then our answer is not right. Then I bet you our 17.25 is correct. Because I was like, we did it last time. So D3 is 8. Thank you. Or D3, I can leave this up here. I'm so sorry. This should be 8 inches. See, that's why I have you guys do it. I didn't do that on purpose. So is it 17.25 then? I think it's going to be. That should be the right answer. Do it one more time. Sorry. Yeah. So did everybody catch that? I had accidentally put 3 for diameter 3. It's actually 8. Is it 17 and a quarter then? 17 and a quarter. Thank you, Aaliyah. Yep. Awesome. James got that too. Sorry about that. Keeping you guys on your toes. 17.25. Yep. Cool. Sorry about that. 17.25. That's official. So that's the difference from the input center in gear number 2 to the output center, gear number 8. Okay. So that's one part of this problem. Now we need to figure out what is the angular velocity of gear number 8. So we know that the train value is equal to the input of the entire train, which is W2, over the output of the entire train, which is going to be W8. Okay. So in this problem right here, we know what W2 is. We can figure out the train value, so we will, and then that's how we're going to get to W8, all right? So if we expand out using those diameters, the train value is going to be equal to minus the velocity ratio of number 1 times the velocity ratio of the second reduction times the velocity ratio of the third reduction. And I think we have a fourth reduction, right? The fourth reduction, yes. So now, using those diameters, we're going to have a negative D3 over D2 times a negative D4 over D5 times a negative D5 over D6, yes, D5 over D6 times a negative D7 over, I'm sorry, D8 over D7. No, I was thinking. So 4 velocity ratios, right? Gears on top for each of those and pinions in their respective velocity ratio underneath. So now we can put our values in. So we can say negative D3. So that's going to be 8 inches divided by 1 inch times negative D4, which is 1.5 inches divided by 5 inches. And then we've got, oh no, I did that the wrong way here. I'm so sorry. I'm so sorry. I have the 5s messed up. So if we look up here, the larger number has to go on top. So D5 is 5 inches because it has to be the gear in the set. So 5 inches on top for a second velocity ratio and 1.5 in the bottom. Everybody get that correction? And then D6 is larger than D5. So 6 goes on top, 5 goes on the bottom. So always the gear, the larger on the top. So this is going to be minus 5.5 inches divided by 5 inches. So in the set, the larger one always goes on top, the smaller one goes on the bottom. And then D8 is going to be 7 inches. And D7 is 1.5 inches. I'm going to double check it. It looks like it's right. So yeah, make sure that you flip 2 and 3 and then get the right ones on top and bottom. So multiplying those out, our train value is going to be a positive value this time. So that means our input is going to go in the same direction as our output. And that number should be, let's see. Anybody get a value for that yet? 136.89. So what that means is W8 will go in the same direction as W2. Okay, that's what the positive means. The input is in the same direction as the output because there's a positive value here. That's why, positive value. Okay, so if we go back up here, we now know our train value. We just calculated it. So our only unknown here is going to be our W8. So we can simply, W8 is equal to W2 divided by that train value. So we know that W2 is 1200 RPMs divided by 136.89. And it's a positive value. So we don't have to, add a negative there. So our W8 should come out to be, and please do verify this, 8.77 RPM. And then it's going to be counterclockwise, which is in the same direction as W2. Anybody else get that same value? Chris did, Josh did. Okay, excellent. Right. This is just like your last problem in your homework. Okay, there's going to be an idler. So the key on that one is to just make sure that you add the diameter. And in this equation, if you wanted to cancel out the fives and multiply across the top, divide by the bottom to just give you less numbers to deal with, you can do that too. Okay. So we see that it doesn't make a difference in the train value, but it does add to the center distance and it does change the final direction of the output speed. And that's the reason you have it. So if you would stack these together and you have 3 velocity reductions and you're like, crap, I want the output to go in the same direction of the input, you just add an idler. That's it. Okay. And the only thing it impacts is that direction and the center distance. Okay. So that brings us to the end of what I wanted to share with you as far as information in chapter 10. You are now ready to do all of the homework problems. Okay. So what I'm going to do is I'll leave this here for a second and we are going to stop the recording and I'll be back with an overview of the homework assignment.